And we're back. Let's see where we left off. Measurement of heat. We were talking about heat before, heat being a form of energy, or technically transfer of energy. So when we talk about heat flow, it's kind of actually redundant, but we tend to say that anyway because we tend to equate heat with energy, even though it actually technically refers to the flow of energy. We need to be able to measure heat or energy. So obviously that involves units. So we need to get familiar with some of the units of heat or energy. The first one that we'll mention is the older one, the one that's been used for a longer period of time, and the one that's probably more familiar, and that is the calorie. Calorie is a unit of energy or heat, and it's a metric unit, so that you can use metric prefixes with the unit of calorie. The symbol for calorie is a lowercase c, and we'll see in a moment why that's important. And the one calorie is the energy required to raise the temperature of 1 milliliter or 1 gram of water by 1 degree Celsius or 1 Kelvin, because 1 milliliter and 1 gram are the same for water, and 1 degree Celsius and 1 Kelvin are also the same for everything. Okay, so that's a very nice, easy, straightforward definition. And it's related to a substance that we're all very familiar with. But it causes problems in some calculations. And so there's another unit that we'll get to in just a moment, which is now actually used more often in chemistry and physics, at least, for measurement of energy. There's also the capital C calorie, and that is the dietary calorie. So when we talk about food having so many calories, a can of Coke has 160 calories or whatever it is, that's actually capital C calories. And each of those calories is equal to 1,000 of the small c calories, or in other words, 1 kilocalorie, which can be abbreviated as kcal, KCAL. That means 1 kilocalorie or 1,000 calories. And the reason they tend to use capital C calories for food is because food contains a lot of energy, and the calorie, small c calorie anyway, is a fairly small unit. So that 160 calorie with a capital C can of Coke would be 160,000 small c calories. And so you can see why they decided to use the capital C instead. Now, the unit that's actually used more often in chemistry and physics today is the joule. The joule is the official SI unit for energy or heat. And the unit was devised because it fits in better with the other SI units and can be used in a lot of different equations to give you results that are also in SI units, unlike the calorie. The energy, oh, I thought I wrote that in somewhere, but anyway. First things first, how do they relate to each other? 1 calorie is 4.184 joules. And that's a well-known conversion factor. You can find that all kinds of places. I'm sure it's in the book, or you can look it up. And so a joule actually ends up being even smaller than a calorie. A joule is about a quarter of a calorie. So we have to get used to ending up with fairly large numbers for joules, even when we're dealing with situations that are not all that outlandish in terms of heat change or things like that. Officially, a joule is defined as the energy required to move an object a distance of 1 meter with a force of 1 Newton. A Newton is the SI metric unit for force. So a Newton would be kind of the metric version of pounds. Like in the English system, pounds are a unit of force. When you think of your weight, what you're measuring actually is the force of your mass being pulled down toward the earth by gravity. And that is actually a force. Your weight is a force. You can exert forces in other directions too, not necessarily just downward. If you took a bathroom scale and stand on it, you got a certain number because of your weight. if you took a bathroom scale and mounted it on a wall and leaned against it, you'd get a certain number because of the force you're exerting sideways. So pounds can be used to measure force in any direction. It's just that we usually do use it downward. Joules would be the metric equivalent, or sorry, not joules, but newtons. Newtons would be the metric equivalent. And so technically, if you want to talk about your weight in metric units, you would want to talk about newtons rather than kilograms, because remember, kilograms are a unit of mass, newtons are a unit of force, and weight is a force. Okay, 1 Newton, if you really want to know, is equal to 1 kilogram meter per second squared. Okay, so, and in fact, those units come just from the fact that you're moving the object 1 meter, there's your meter, and an energy of, an object 1 meter of 1 kilogram, and yeah, okay. So a Newton, so rather a joule, a joule would be 1 kilogram meter squared per second squared, because a joule is a Newton meter. That is, a Newton is 1 kilogram meter per second squared, and you're moving the object 1 meter. So when you take this times meters, you get kilogram meter squared per second squared. Or you can also call the joule a Newton meter. But we'll just call them joules. The symbol for joule is J. It is a metric unit, so you can use metric prefixes with joules. Oh, there it is right there. I missed it. So you can use metric prefixes with joules. And so since a joule is such a small unit, we often end up talking about kilojoules, thousands of joules. So we'll change a lot of our answers to kilojoules in the near future. Okay, so kilojoule is 1,000 joules. Now, on the subject of heat capacity, for any given object, you can find a relationship between how much energy you add to it and how much the temperature changes. And that relationship is always the same for that particular object. So you add, say, 1,000 joules to an object and the temperature goes up 5 degrees. If you add twice as much energy, the temperature should go up twice as much. So, 5,000 joules divided by 1,000 joules divided by 5 degrees would be the same as 2,000 joules divided by 10 degrees. And you end up with the same number. That number is what's called the heat capacity. Heat capacity is the energy required to raise the temperature of an object by each degree Celsius or Kelvin, if you prefer. And it's defined as just C, and here we're talking about capital C, is equal to Q, which is the amount of heat or energy divided by the change in temperature. So Q is the heat or the energy in joules. Delta T would be the temperature change, usually in degrees Celsius. And so the units would normally be joules per degree Celsius. All right. Since this is a 3-term equation, we can set up one of our little triangles in case we need to rearrange it, hint, hint, where we have C is equal to Q over T. So C goes in the lower left-hand corner, Q goes on top, and delta T goes in the lower right. C is Q over T. And now that makes it easier for us to rearrange it. But we'll set that aside for a moment and come back to it. Heat capacity is normally used for an object or a specific amount of a substance in a sample. Capital C, heat capacity, is often used if you have an object or a sample that's always the same substance and always the same size. Like if you're doing experiments in a calorimeter, and it's always the same calorimeter and it's always the same mass and always made of the same materials, then you'll often use heat capacity to account for how much energy is expended in changing the temperature of the calorimeter by a certain amount. Each substance has its own value for heat capacity, but remember, the heat capacity is also affected by how much of the substance you have. So like in that example of the calorimeter, if the mass of the calorimeter changes, or if a piece falls off it or something, then you're going to have to find the heat capacity again, because if the mass changes, the heat capacity changes. And that makes it an extensive property. In other words, it depends on how much of the stuff you have. And as it turns out, the heat capacity is directly proportional to the amount of the stuff that you've got, usually expressed in mass. So some examples of what you can do with this equation. Would be, for example, if the heat capacity, now, since heat capacities are already known for given substances, we don't do the equation in this original form very often, because as long as we know what the substance is, we can look up the heat capacity. We don't need to calculate it. Very often what you'll do is rearrange the equation to find one of these other things when the heat capacity and the other term is known. So for example, if the heat capacity of a fireplace poker is 285 joules per degree Celsius, how much energy is required to raise its temperature by 125 degrees Celsius? Well, energy is Q, or because energy, of course, is also heat. Okay, so if C equals Q over T, then Q must be C times delta T. Okay, C equals Q times delta T. So Q would be 235 joules per 1 degree Celsius times 125 degrees Celsius. Notice the degrees Celsius cancel, and that leaves you with joules as the only unit left, and you get 35,625 joules. That's a little over the top on significant figures, so it looks like we should cut it down to 3, because that's 3 and that's 3 significant figures. So you could call it 36,000 or 35,600 joules, or 35.6 kilojoules. And this is a nicer number, so I decided to do it that way. So 35.6 kilojoules is the amount of energy it takes to raise the temperature of that fireplace poker by 125 degrees Celsius. And another thing you can do, of course, is calculate how much a temperature should change if you know C and Q. So say if 1183 joules of energy is withdrawn from a pan with a heat capacity of 375 joules per degree Celsius, how much does this temperature decrease? Because we've been talking so far mostly about adding heat to things and having the temperature go up, but it's equally true that you can withdraw heat from something and have the temperature go down. And so this equation works in both cases. So if C equals Q over T, delta T that is, then delta T must be Q over C. Okay, Q over C. And to make it clearer how the units work out, I'm going to take advantage of the fact that Q over C is the same as Q times 1 over C. All right. So delta T should be Q, which is 1183 joules, times C is 375 joules per degree Celsius. 1 over C would just be that flipped upside down. So 1 degree Celsius for every 375 joules. Now you'll notice the joules cancel as a unit and leaving you with degrees Celsius as the unit. That's good. 1,183 divided by 375 is 3.15. So that's how much the temperature should go down. Not too bad. All right, moving on, the specific heat. Now, the book calls it specific heat capacity. So I included that word the first time, but most books refer to it as specific heat. And so that's what I'm going to call it. The specific part means that it's specific to the amount of substance present. That's usually what the word specific means when it's added to the name of a quantity. It just means that you're basically taking into account how much of the stuff there is. And in this case, it takes into account the fact that specific heat, or that, sorry, that heat capacity depends on the amount of the substance present. Okay, so specific heat is the energy or the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Or on the other hand, it works the other way around too. It's the energy that would have to be removed in order to decrease the temperature of 1 gram of a substance by 1 degree Celsius. And the advantage to this is that it allows you to compare substances sort of on the same level, because in each case you're comparing 1 gram of each substance to any other substance if you're looking at a table that has values for specific heats in it. And also it allows you to do calculations that involve various amounts of the given substances. If you're using heat capacity, then you're pretty much stuck using whatever amount you originally found the heat capacity for, and you can't change the size or the amount of the substance you're dealing with. If you're dealing with specific heat, you can change the amount of substance you're dealing with as much as you want, because mass is part of the equation. Okay, and as it turns out, each substance has its own unique value for specific heat. And that means that you can, in some cases, identify a substance or at least narrow down what it might be by finding its heat capacity and comparing it to known values. Because, since every substance has its own unique value for specific heat, that means basically by this time they're all known and they're all listed in tables. So if you want to know whether a piece of metal is tin or iron, you could find out its heat capacity through an experiment like these and find out what the number is and look at the table and see whether it's closer to the specific heat for tin or iron. And if it's, with any luck, it'll be exactly the same as one of them. And if it's not, then there was some experimental error, but generally whichever one it's closer to, that would be the one you choose. So in this case, specific heat, different books use different symbols for it. Ours is deciding to call it lowercase c. So specific heat is little c. That's why I put the little tail on it there. And that is Q over M times delta T. So it's the heat or energy in joules divided by the mass, usually in grams, times the change in temperature in degrees Celsius. Since now we're accounting for the amount of substance present, this is an intensive property. It doesn't matter how much of the substance you've got, because you're going to take care of that by putting the mass in the equation. Now, we can also rearrange the equation to find these other things, because like I said, if you know what the substance is, then you can look up C. You don't need to calculate it. So very often we'll know what the substance is, and therefore we'll know what C is, and we'll want to find Q or M or delta T. As long as we know all of the other stuff, we can find any one of those. Unfortunately, this is a 4-term equation, so we can't use our little triangle to rearrange things. So we're going to have to rely on algebra to do that. So a good example of that might be, say, if an iron frying pan with a specific heat of 0.449 joules per gram degrees Celsius and a mass of 950 grams increases in temperature by 180 degrees Celsius how much energy has been absorbed. All right. So we take this equation, C equals Q over M times delta T, and we have to solve it for Q. Solving for Q, of course, means that we want to get Q alone on one side or the other of the equation. Q, as we start out, is divided by M times delta T. So if we multiply the right-hand side by M times delta T, it'll cancel out the M delta T in the denominator. But to keep the equation equal, we have to multiply the right-hand side, or the left-hand side rather, by M delta T also. So we have M delta T C is equal to Q. And that's what I ended up over here. I put it in a different order, but of course you can multiply in any order, so that's okay. Q is equal to Cm delta T, or M delta Tc, or MC delta T, which is the way we're usually going to write the equation in the future. And so you just take those three numbers and multiply them by each other. The specific heat of iron was 0.449 joules per gram degree Celsius. The mass of the pan was 950 grams. Whoops, there should be a decimal point there. And the change in temperature is 180 degrees Celsius. Notice that grams in the mass cancels with grams in the units of C, and degrees Celsius in the units of the temperature also cancels with degrees Celsius in the units of C, leaving us with joules as the only remaining unit. And that's good because we're looking for energy, which is joules. So 0.449 times 950 times 180 is 76,779 joules. You could write that as 76,800 joules with no decimal point. That would be three significant figures, but I chose to make it 76.8 kilojoules because that looks nicer. Okay, another possible example. What if you want to know the change in temperature? If you know what the substance is, and therefore you know its specific heat, you should be able to calculate what the change in temperature should be if you know how much energy is being added or taken away without even having to do the experiment. So if 3,586 joules of energy is added to an aluminum pan, and the specific heat of aluminum is 0.903 joules per gram degree Celsius, and the pan has a mass of 797 grams, how much does its temperature increase? Well, we have if C, again, if C equals Q over M delta T, and we want to solve for delta T, well, that's actually fairly easy because when you're solving for something that's in the denominator of a fraction, you can just switch it with whatever's on the other side of the equation. So we switch delta T with C, and we end up with delta T equals Q over M times C. And that's exactly what we got here. Delta T is Q over C times M or M times C. It doesn't matter which order you do it in. In order to make the units clearer, I'm going to consider this to be equivalent to Q times 1 over C times 1 over M. That means the same thing, but it'll make the units easier to follow. So delta T should be 3,586 joules. And that's in the numerator. I just put a 1 in the bottom to make it clear that that's in the numerator. Times 1 over C. C was 0.903 joules over grams degrees Celsius. When you turn that upside down, it becomes 1 gram times 1 degree Celsius over 0.903 joules. And then 1 over the mass is 1 over 797 grams. You may notice here that joules in the denominator of 1 over C now cancels with joules in Q, and grams in the denominator of 1 over the mass cancels with grams in the numerator for 1 over C, leaving us with degrees Celsius as the only unit left. And when we do the math, it's 3,586 divided by 0.903 equals, and then divided by 797, comes out to 4.98 degrees Celsius. That's how much the temperature should change. Okay, and I see we've arrived at about 25 minutes, so I'm going to stop there for segment B and start up with segment C in just a moment.